Hello guys, welcome to the Dynamics of Dark Energy, and this is Sudham Leonardo Cap, and we are starting with section 2, in which we are going to see what are the elements of Flrw cosmology, whereas Flrw signifies you the isotropic homogeneous universe where everything at the large scale appears to be same whenever you will look at the universe. So this cosmology have been first introduced by Friedmann, Lemaitre, Robertson, Walker, and hence this is called the Flrw cosmology. So what we are going to learn in this section, the dynamics of universe is described by Einstein equations, which are in general complicated nonlinear equations, as you can see here. Now this is Einstein's equation where this part signifies you the geometry part and this is corresponds to matter section. Now these equations look like, what is the meaning of these equations? So these are actually differential equation and they are second order differential equation, but they are not linear, or basically they are highly non-linear, and hence from the mathematical point of view, these equations are very complex. However, they exhibit simple analytical solutions in the presence of generic symmetry. But if you will invoke any kind of symmetry, then you will get a very simplified solutions analytically. The Friedmann-Robertson-Walker Flrw metric is based upon the assumptions of homogeneity and isotropy of universe, which is approximately true on large scale. Now, since we are in cosmologists, therefore, we don't have any problem with this approximation. The small deviation from homogeneity at early epochs played a very important role in the dynamical history of our universe. These are very important keywords and you have to stress on that. Small initial density perturbations grew via gravitational instability into the structure we see today in the universe. So what is the key role of inhomogeneity in the universe? This inhomogeneity is called the initial perturbations from the inflation. So we are assuming that the early universe was not too much homogeneous. There was some inhomogeneity, and this inhomogeneity makes the large scale structure what it is. Hence, this large scale structure, as the universe grow up, from the gravitational instability, they form structures what we are seeing in the universe. The temperature anisotropies observed in cosmic microwave background. We had earlier talked about cosmic microwave background, and we see that the temperature is not isotropic. Isotropic means that not everywhere is same. Somewhere the temperature is very much cool, somewhere it is hot, and somewhere it is too much hot. Therefore, this is called the anisotropy in the temperature. Hence, we see that these anisotropies in CMB background are believed to have originated from quantum fluctuations generated during inflationary stage in the early universe. So where these fluctuations come from? From this inflation, when the universe was quantum stage. From there, the evolution of fluctuations came and entered to our universe. For details on density perturbation predicted by inflationary cosmology, you can refer to these references. In this section, we shall review the main feature of homogeneous and isotropic cosmology necessary for the subsequent section. In this section, we will understand what is Flrw metric, what is the meaning of isotropic and homogeneous, and what are the Einstein's field equation for corresponding this metric. With this review, I am expecting that you know some part of general relativity, and if you don't know, you will understand, no problem. In Einstein general relativity, the one component is called metric. In this metric, it is basically of the structure of 4x4 matrix, where the zeroth component shows the time component and the rest are showing you the space component. Now this metric is actually the space-time matrix, and how the metric in which metric we are. So suppose in the 3 dimension of Eulerian geometry, we are writing the equation of, suppose you are want to define the distance bit of this line, you can simply define this distance by dx square is dx square plus dy square plus dz square. Now in the 4 dimension, this will have the definition of d square is equal to minus c square dt square, because ds square has the dimension of distance, and we know distance is equal to speed into time. So this is for the time component, and the rest is a spatial component. Okay, so this is actually the component of g mu will be, so first component will be minus c square, the second component will be 1, third component will be 1, and fourth component is 1. So this is the how we are extracting from this length element. We will find out what is g mu nu, and g mu nu is a dimensionless quantity. For the FLRW, they have chosen that our universe is homogeneous and isotropic, and we know the homogeneous and isotropic, if we see anywhere the universe looks same. So therefore it has a spherical kind of symmetry. So in spatial dimensions, wherever we see we have some symmetry, therefore we know we have c is equal to 1, therefore this has only time quantity like minus dt square, plus there is a scale factor which I have explained in my first lecture, you can see from the I button. And then this shows you that r square d theta square and sine square d phi square, these are the angular component, and this angular component shows that it has some spherical kind of symmetry. Wherever we see, we will find it, isotropic and homogeneous. And this is an spatial, where your radius part, this is radial part, they are actually expanding. This k is showing you the curvature of the universe. If k is equal to 0, this means you have in flat geometry. If k is 1, therefore the geometry of the universe is kind of a spherical one. And if k is minus 1, therefore the geometry is hyperbolic kind of things. These are hyperbolic geometry. K is equal to 1, like spherical kind of geometry. Here is the geometry of sphere. So there have some different meaning, and if you know more about it, you can see the lectures on general relativity. So we understand what is ds square, where a of t is a scale factor of cosmic time. Suppose t is the cosmic time, where a is telling you that how the universe is basically expanding. So suppose we are talking about this sphere which is corresponds to our universe, and then another universe. So the thing is that suppose in this universe, as the universe is getting bigger, so r is the actual distance, and a basically tells you that a is associated with r. So a is the scale factor through which r is giving you the actual distance between 2 points. Suppose here are 2 points, this is called r, the actual distance. But as universe is getting bigger and bigger, so here is the distance, whatever they will be same, but since the whole room or whole universe is basically stretching out, therefore this a is responsible that these points will go again further. So a is called a scale factor. The coordinate r, theta and phi are known as co-moving coordinates. A freely moving particle comes to rest in these coordinates. So if a particle is moving freely, so if you are using these kind of coordinates which are called co-moving coordinates, the particle can come to in rest. But as we know, the universe are never resting because it is already accelerating, it's expanding. Therefore the a of any moving particle cannot be in rest, so a cannot be 0. Hence the moving particle cannot be 0 if we are actually measuring in terms of a. But if you are measuring in terms of r, theta and phi, then a particle can come to in rest, and this kind of coordinates is called co-moving coordinate. Equation 1 is purely kinematic statement, and in this problem the dynamics is associated with scale factor at. So whatever the dynamics will show the at, because as you can see r is not a function of time, theta is not a function of time, and phi is also not a function of time. So what is the function of time is a. So if you integrate this ds square, they will always be same. So what we're gonna integrate, the integration will goes to this part. Hence all the dynamics is associated with a. So whenever you are seeing the dynamics in space time, it is because solely from the scale factor. Einstein equation allows us to determine the scale factor provided the matter content of the universe is specified. So if you give, because in Einstein equation, suppose G mu nu is the metric part and here it is T mu nu. So T mu nu containing the matter dominated. If you will give the matter dominated part here, then it will tell you how the metric is. So now G mu nu contains your scale factor. Therefore, to determine how this scale factor, you need to first invoke what is your T mu nu. So if you don't have T mu nu, you cannot determine A of T. But we can have T mu nu. Suppose you don't know anything about T mu nu, you can take it as constant or you can make it to 0. So we are living in a space where there is nothing, the 0. So the space is completely vacuum. So how that A of T will play out? Now if T mu nu is constant, suppose there is the whole universe is filled with some constant kind of matter field, how this A of T will play out? So in this sense we will extract all the dynamics of A and T, A of T. The constant K in the metric describes the geometry of a spatial section of a space-time with closed flat open universe. So K is 1 is closed universe, 0 is flat universe, and minus 1 for the open universe, as I have described you. Plus 1 for sphere, spherical type of thing, since sphere is kind of very closed one. 0 is flat because it is flat, and minus 1 is hyperbolic. So universe is kind of an open one, it will never end. So we can now change whatever we have seen equation 1, we can change the r, theta and phi in such a way that we can write r. Okay, so what we can change that, okay, let theta be theta and phi to be phi. Let us change r in terms of chi in another metric in such a way that whatever you are seeing in the denominator, it can be removed. Now if you want to remove, it means that they have defined like this, 1 minus k r squared in terms of d chi square. Now if you will define in this sense, therefore we will have some kind of a functional form here. Okay, so you can choose k, you can integrate it here. Now dr squared over d, let us say it is dr, no, not dx. Okay, so here you have. Now since we are working with dx and everything, just determine k. Suppose k is equal to 0, therefore dx is r, or integrate x is equal to just r. Okay, so r becomes chi. Now if k becomes minus 1, therefore 1 plus r square, and 1 plus r square, if you integrate, you will get sine hyperbolic of x. And if 1 minus kappa is 1 minus r square integrate square root, and if you integrate, then you will get sine of chi. So it means that we can transform r in terms of chi. Hence we have got this kind of functional form here, that first of all we are writing dr in terms of dx, d chi square, and then we will get from based on the curvature, we will get the functional form of the curvature. For flat universe, this is chi square, and then it will get simply multiplied by d theta square and sine square d phi square. So that is the whole gameplay here. Now our job is to find what is the evolution equation, or what is the equation of motion. Now since we have the metric, now if you determine what is G mu nu, now there is no any way we can determine what is G mu nu, so we have to first guess that what could be G mu nu. Now our guess was equation number 1, and then we have transformed and found out the another ds square, which is again showing you for different purpose how your metric will look like. So from where we will get what is G mu nu. And when we got G mu nu, then we can extract from G mu nu what will be R mu nu, what is R. So the differential equation of scale factor and matter density follow Einstein equation. So in Einstein equation, I have already told you that G mu nu is called Einstein tensor, and this is defined to be R mu nu minus half G mu nu and R. This is called Riemann tensor, and this is called Riemann scalar. So they are encapsulated in the Einstein tensor is denoted by G mu nu. So now you can also play with indices. These are called indices. If my indices are like this, G mu nu is then R mu nu minus half, then this will become canonical delta, G mu nu, and then R. Now if your left hand side is this way, therefore right hand side must be follow like this. So in the in the idea of Einstein, the equations, all the physics must be covariant. And what is the meaning of covariant? When you are translating the idea of covariance in the tensor form, it will follow the indices. So whatever the indices in left side, it must be equal, it has the same structure in the right hand side. So you cannot equate, like suppose G mu nu here, and you cannot do it like lambda. No, it is not possible. Either you have to add like, okay, I'm going to add delta mu nu, or I am going to add like some kind of an arbitrary tensor of kind mu nu. So then and then only this equation will hold true. Otherwise you will establish, if you will not invoke this thing, means that mathematically your equation is incorrect. So that is the beautiful thing about tensors, that whenever you are writing everything in terms of tensors, the tensor indices will take place, that are your equations correct or not. So whenever you will do research, make sure your indices is in same footing. Now since we have understood that part, now we have to extract what could be R00, what is R. Means R00, Rij, they are basically telling you what are the components. Now R mu nu is again a 4x4 metric, hence therefore this is like this one, 00 and this one. So 00 means that they are talking about this component. Rij means talking about it R11. So which one be R1? This is corresponds to, suppose I am writing here like 0. So suppose it is 0, 1, 2, 3. This is the row, this is the column of 0, 1, 2, 3. This is the row 0, 1, 2, 3. So 0, 0 is going to give you this component. Hence 1, 1 is going to give you this one, 2, 2 will actually give you this component, and 3, 3 will give you this component. Suppose if I am talking about 2, 1 will give you this one, but 1, 2 will give you this portion. So you have to read it, that what is it's talking about. Rij is talking about this portion, that okay, now we are in the spatial part. So therefore the Riemann tensor is giving you that zeroth component of Riemann tensor has that a double dot. So dA over dt gives you velocity, and d2a over dt square gives you some acceleration. So now this equation tells you some kind of an acceleration in the scale factor. Now Rij is giving you, it has some acceleration, again it has velocity term, and again it will contain some k part. Okay, and k is corresponds to some amount of curvature. And now since you can see here Rij, therefore they have invoked delta Ij. It means that now tensorially they are correct. Now R is an scalar quantity because it doesn't have any kind of tensors. So this is called, that's why it is called Riemann scalar. And Riemann scalar will contain this thing without any tensor. So they are multiplying with 6 and you have this component. Now when we are talking about energy momentum tensor for the matter field, so what is the meaning of energy momentum tensor of matter field? Now since in the language of tensor, T mu nu again consists of this whole matrix part, but this metric part for the zeroth component we will have minus of rho, and all the off diagonal components are 0. Similarly for spatial part, the diagonal part will survive and there will not be any off diagonal portion. So this is called, if you're treating the matter portion, whatever the matter content like galaxy, photons, baryons, all leptons, hadrons, everything, we are taking it, suppose, because universe is very huge, and let us take every matter component just like in fluid. So what we are approximating the matter content of the universe as a fluid part, and this fluid part have energy density and the pressure part. And if you know the energy density and pressure part of the universe, then thermodynamically we can find the thermodynamic first equation, everything we can define it. We can define the free energy of this fluid, we can define the enthalpy of this fluid, we can also define what is the heat loss and heat gain in this in this fluid. So that is the concept of fluid. Therefore the space time is linked with thermodynamics. Now you have already told you that the temperature, there exists a temperature of universe. Now today the universe is about 2.5 Kelvin cool. The early universe was very hot, very dense. Therefore, whenever we are talking about the structure of the universe, we also somehow indicating the thermodynamical properties of the matter. So that's why we are taking the energy momentum tensor of the fluid. And what is the best possible way to take the fluid? We are taking is at, okay, we can have the energy density and the pressure, and that is enough to thermodynamically we can derive everything about this fluid. Okay, now when we invoke this thing in the Einstein's field equation and right hand side this one, we will see that we can define Hubble parameter and Hubble acceleration. So this the Hubble scientists have defined like what is the velocity in terms of scale factor of with ratio to scale factor, and then they have defined it, okay, if you take one more derivative of this, then we will call it as Hubble acceleration or Hubble. So this is again in terms of Hubble velocity, and this is called Hubble acceleration. Okay, so the Hubble factor h square from the Einstein's field equation, like if you have only 0 component, this 0 component will give you a dot by a square. Now you can see in the equation number 7, equation number 6 or 7, if you invoke this and this, then from here, and you can see here, so if you will invoke 5 and 7, okay, from here this part and this part, they will cancel out each other, hence therefore you will just left with this a dot by a square. So from here, from equation 9, we will understand that in the right hand side you have this rho energy density part, and there is some density from the curvature. If space time is a curvature, it may have some kind of density which is called as the curvature density. Okay, so the right hand side has taken care by the matter density, and left hand side is giving you the Hubble constant, and this Hubble is determines you that what is the rate at which our universe is accelerating, as I told you in the first lecture. So this is from the equation 1. Now if you will solve the Rij part of Friedmann equation, then you will get this time parameter of time derivative of Hubble parameter, which gives you that Hubble acceleration, that how is accelerating, how the Hubble is actually expanding. And through 9 and 10 you will understand what is the gameplay here. Like the 9 is corresponds to only energy density, there is no role of pressure here. So if you have any energy density in the universe, you can replace with rho. So rho can contain a different type of energy, like energy from rho lambda. So you can define that I have rho total, rho lambda plus rho matter plus rho some kind of radiation, for example rho some kind of any scalar field, and blah blah blah, anything you can add here. Now in the second equation you have the pressure of whatever the fluid you have and whatever the energy density you have. So here H is Hubble parameter, rho and P denotes the total energy density and pressure. The energy momentum tensor is conserved by virtue of Bianchi identities. So you know G mu nu is equal to kappa square T nu mu, and there is again there is called Bianchi identity. What does it imply about Bianchi identity? It says that this always be true. Like if you covariant, this is called the covariant derivative. Okay, if you will have the covariant derivative like T nu, G mu, they have to be always be 0, and this can be proved from the analysis of tensor, that you can do it from the cyclic analysis, sometimes G nu, G mu, and you can again write it in terms of an different way, and you will reach at that. With this, our energy momentum tensor of the matter component is always 0, which says you that whatever the matter component, whatever the matter exists in our universe, they have to be conserved. Now from mathematical point of view, this is called from Bianchi identities, and we already know that this has to be conserved. So if you are working in any kind of metric, this solely need to be true. It every time it holds good. So no matter what are the components is actually playing in your system, the Bianchi identity must hold true in every possible way. But there are somewhere there this Bianchi identity does not hold, and where the metric is torsion, metric have some torsion. Okay, so in the torsionless metric this is always hold good, but if you have torsion in your metric then this may fail, and we will then envisage that okay, the energy momentum tensor must be conserved, then in some sense this has to be hold true. So these are the very technicalities of the subject, and you will understand later on what does it mean. But for the dark energy related, we don't need to go in the depth. So this equation tells you that rho dot is d rho over dt plus 3h rho plus v. This you have encountered in the fluid mechanics in your 11th or 12th, that where the fluid is conserved. Suppose you have the fluid is going through one point, and obviously the amount of fluid is entering here, that amount of fluid will actually extracting here. This is called also the conservation of fluid. So similarly here it shows that the fluid must be conserved as the universe is actually expanding. So the rho is the rho will also change with time, therefore the d rho by dt plus 3h, it has some Hubble parameter, and rho plus p. So in some sense we have three equations, equation 9, equation 10 and equation 11, and from here you can do everything. Now equation 11 can be derived from equation 9 and 10, yes, which means that two equations 9 and 10 and 11 are independent. These three equations, these equation 11 and 10, they are dependent. 9 and 11 they are dependent. Okay, so it means that these two equations have to be independent. Among these equations, the two equations are independent. So in three equations only two equations are independent. So what you have to think that which can be independent or dependent. So for our scenario the play is very simple and clean. Now if you want to eliminate the curvature term, the curvature density, then from equation 9 and 10 we will get the relation with this a double dot by a. Simply the scale factor acceleration is equal to 4 pi g by 3 rho plus 3p. And now when acceleration can happen, now if rho plus 3p is less than 0, then we can say that this is called acceleration, because we can already see from the classical mechanics point of view a is equal to dv over dt, and if v is positive and if the rate of change in time gives you the velocity to be positive, it means that the block or the mass is accelerating, and if v is less than 0 or any change it turn out to be negative, it means that the motion is actually deaccelerating. So when the universe can be accelerating, from here we can to fact that okay, this rho plus 3p has to be less than 0 because negative is already there. So if they are negative, what does it imply? It implies that rho must be less than minus of 3p, correct? So this says that p over rho has to be greater than what? Minus 1 by 3. Okay, so p over rho is always be minus 1 by 3. So if you want to have the acceleration in your system, from here the relation is that the pressure of the fluid and the energy density, the ratio of them in such a way that it has to be always greater than minus 1 by 3. Now if you have the fluid pressure and density in such a way that they have to be always greater than minus 1 by 3, what does it mean? It means that if you will get like suppose minus 1 here, so minus 1 by 3 is obviously lesser than minus 1. Why? Because negative will cancel out, therefore 1 by 3 is always less than 1, or 1 is greater than 1 by 3. Now as you got the relation between a double dot by a in terms of this, so from equation 9 here says you that if you know the rho and if you know this play, then you can define k in terms of critical density like omega of t, and omega of t is called dimensionless parameter for energy density in terms of critical density. Rho t, omega of t minus 1 is equal to kappa over ah square. How it has been defined? Well, you can simply divide by h squared. So 8 pi g over 3h squared is labeled as rho critical. Okay, So rho critical is 3h square over 8 pi g is the critical density, and if you divide everything and make it to dimensionless, so from here you will get that okay, whatever the omega t you have, omega t is that it is apparently time dependent. So how it can be time dependent? You can see that this will be here 1 and rho over rho c, and rho over rho c to be termed as omega of t minus kappa over a square h square. So this kappa over a square is called as the curvature density, whatever. So we can see here kappa k over, not kappa, k over a square h square is omega of t minus of 1. So this omega of t minus of 1 actually deals with the dimensionless quantity. And now we can see what we can get from here. So if the omega is greater than 1, so if omega is greater than 1, we have already understood from here. Now you can see here that if k is 1, the universe is spherical type, k is 0 flat 1, k is minus 1 open type. Now in this here we can see that this is always be positive because it is whole squared. So if k have to be positive, therefore omega of t minus 1 has to be always greater than 0. It means that omega must be greater than 0 throughout the time. Then we can see that the universe is close to 1. Now if k is 0, then this omega is always has to be equal, which says that the energy density must always be equal to critical density. Whenever the universe it is, the universe has to be critically fine-tuned. Now if the k it to be minus 1, that if universe is kind of open 1, then omega toward the time has to be less than 1. This says that whatever the energy density you have, it has to be less than the critical density of any time. So observations have shown that the current universe is very close to especially flat geometry. Therefore omega is to be 1. Hence with this kind of observation we have come to our very simplification idea that we can write simply Flrw universe in terms of minus dt square plus a square and dx square plus dy square and dz square. So we are saying that this universe is like this one x, y and z, just like in plane, and t has some other dimension, 4 dimension. Since it is a flat, therefore we can treat it as like an Eulerian spatial dimension, and t is simply this one, and from here also we will get the whole dynamics. So in so many papers you can see, you can meet with this kind of metric also. Now people are also interested to investigate what will happen if we have different kind of scalar field, what will going to happen if you have different curvatures. So you can also play with abstract key. Okay, now the evolution of universe filled with perfect fluid. We have seen that universe have to be filled with perfect fluid in order to understand how the energy density and pressure will role play. But we have told you about one of the keyword is called equation of state, which is most important. And equation of state is going to give you how the nature of the universe is. So this equation of state is defined as P over the rho. So ratio of pressure to the energy density of the matter part is give you the equation of state. And if omega is to be constant, we are seeing is to be that it is actually depicting the cosmological constant. Now omega should not be constant, omega can be varying with time, okay, or omega can be defined from the scalar field. So this has this can be of the following property of phi, okay, so there can be anything possible. Now if you work with k is equal to 0 means flat universe, therefore we will get the relation from 9 and 10 that h is equal to 2 by 3 into 1 plus omega t minus t naught, and t naught is kind of a constant that we have specified that from t0 is the time at which we are now present, and when we are looking back, the time t is kind of a variable time in which we want to see either future or either in past. Now since observation is whatever we are gaining, the data we are gaining from the past universe, so t is always be kind of lesser than t0 and so on. So sometimes people say that okay, they use the conformal time in order to show the backward time, or we always, so it depends on you that where you want to fix t naught. Sometimes people fix t naught as a present time, sometimes people set the t naught at the past time, that okay, when the universe formed, so we can set it t naught to be 0.1 after the big bang, and then we come to t is equal to now at present time, so that h will be constant or positive constant. Okay, now a of t, the scale factor, will turn out to be in the time relation t minus t0 to be 2 by 3 plus 1 over omega. And now if omega is minus 1, it says that p is equal to minus of rho. Okay, p is equal to minus of rho, it says that this universe is now accelerating. So if omega is 0, it means that the matter, it is called matter fluid. Omega is 1 by third, it means that it is giving you the radiation type fluid. Omega is 1, the fluid is not the fluid which we are encounter, it is called an stiff fluid. And if omega is less than minus 1 by 3, like minus, it is called minus 0.33, suppose it is less than like minus 0.66 or 0.8 or minus 1, so whatever you will get, these are for the accelerating kind of fluid which gives the accelerating in the universe. Now from which rho is actually depend on its scale factor, like this, rho is proportional to 2 minus 3 into 1 plus omega, and from this omega they change. Suppose omega is equal to 0, therefore rho will turn out to be e to the power minus 3, and if it is omega is 1 by third, therefore rho is proportional to e to the power minus 4. And suppose if omega is turned out to be minus 1, then it is proportional to constant. So rho is something like rho 0. It is constant, no problem. So they have told you that for radiation type rho this one, and for matter type, dust type, when the pressure is pressureless. So since omega is equal to 0, therefore there is no any pressure of the fluid. So we are assuming that if the fluid is dust type or matter type, it does not create any pressure. So if it does not create any pressure, therefore in the universe there exists a period where the universe is basically not accelerating. They are basically, the acceleration becomes kind of an deaccelerating. So universe have also gone through a phase where it deaccelerates, and then dark energy comes in and kick the universe, and then universe tends to accelerate as we are approaching to now. Z is equal to 1. So Z is corresponds to length of redshift. Okay, from the equation 12, the accelerating happens if a double dot is greater than 0. We have encountered a double dot over a is about rho plus 3p, and this about minus, therefore this has to be less than 0. So omega is always be less than minus 1 by third. So if it is minus 0.33, so everything will be below. In number line, here is 0, here is minus 1, here is minus 2, 0.33 is here, so everything is here is actually lesser than minus 0.33. So if you go beyond minus 1, these regions are called phantom region, where the equation of state crossing minus 1 and minus 1 is called the barrier or phantom barrier. And now the data is suggesting that our universe is so much accelerating that it is basically crossing minus 1. So equation of state is crossing negative of 1. So now from here we will see in the next lecture. Thank you very much.